So the purpose of the missing energy lab is to measure the missing energy of a rolling object, and the materials for this lab are a ramp, a ball, a meter stick, a scale, and a timer.
Okay, so for our report, the first thing that we have is for height number 1, it is 6 centimeters. And then, so the next height for trial 2 is 8 centimeters.
The bicycle was 5 meters, right?
Yeah, but
And our final height for trial 3 is 17 centimeters. So our times are as follows. The time for trial 1 was 4.97 seconds, trial 2 was 3.53 seconds, and trial 3 was 1.86 seconds.
These are the steps to how to find rotational kinetic energy in our energy lab. So to find rotational kinetic energy, we need to solve for velocity because that's a major part of the formula. To solve for velocity, we can use two kinematic equations. The first one is that velocity x squared is equal to velocity naught plus 2 times acceleration times a change in distance, or x. Also, we can use an equation that's x is equal to x naught plus velocity naught plus 1/2 acceleration times time squared. So the first thing that we do is we can simplify these. When the ball rolls down the ramp, it starts from rest, so we can say that velocity naught is 0. So we could just kind of cancel that out and get velocity squared is equal to 2ax times the change in distance. Also from this one, it's the same thing. Velocity naught is 0, so we can simplify that and then solve for acceleration. So acceleration is 2 times a change in distance over time squared. And so as we can see from this diagram down here, the change in x, or the distance, is the length of the ramp. So we can also say that this is 2 times the length of the ramp over the time it takes to roll down squared. So that's how we solve for acceleration. Once we solve for acceleration, which is this, we can plug this into this equation and solve for velocity squared. And then you square root that velocity to get what regular velocity is. So once we solve for velocity, we can plug that into our rotational kinematic equation. So the equation is that potential energy is equal to rotational energy plus translational energy. That happens because the ball is not only spinning this way, but it's also moving that way, so you need both. So to plug in just the formulas for each of those variables, we say that mass times gravity height, which is the potential energy, is equal to rotational kinematic energy plus 1/2 mv squared, which is the regular regular kinetic energy equation. So we can solve for kinetic energy rotational, which is mass gravity height minus 1/2 mass velocity squared, and then we can factor for mass. So you pull out mass, which is the mass of the ball, so we need to find that as well, which is just gravity, which is a constant of 9.8 meters per second squared, times the height, which is the height of the ramp here, minus 1/2 velocity that we find up here squared, is equal to the rotational kinetic energy. So that's how we solve for rotational kinetic energy.
So in conclusion, as our data table shows, an increase in height of the ramp leads to an increase in gravitational potential energy, which thus contributes to a greater rotational kinetic energy.